Hello. So in this section, it's the final section from the first chapter, section 1.6. We're going to look at rationalising denominators. So this is a so that's essentially when we say rationalise denominator, obviously a fraction and denominator. These are fractions with a denominator with a third on the bottom. So for example, root 2. We discussed last time that root 2 is a third, simply because root 2 is not a square number. So that would be an irrational number. That would give me an infinite decimal if you were to put it in the calculator. Unlike say root 1 and root 4, as root 1 would just be 1 and root 4 be 2. This gives us a whole number because 1 and 4 obviously square numbers, so they are not thirds. Okay, and so what we would look at in this section is sort of rationalizing them, so kind of making them not irrational, so basically make them not a third. And the whole idea is essentially we're going to exploit the fact we can times any fraction by a number, say n, but we multiply both top and bottom by the same number. We are allowed to do this because a fraction like this, n over n, is just 1, okay? Because it's the same number cancelling each other out. And in particular, what we're going to look at is um, a particular kind what exactly we're going to multiply. So this is where also our knowledge of difference of two squares are going to come in. So if we have x squared minus a squared, remember when we looked at factorizing, that we can write a difference of two squares, so x squared and a squared, square numbers, right? If we have a difference of in this way, we can refactorize this into these sort of linear factors, right? Of x minus a and x plus a. And why is that important? Well, we can exploit this because, for example, say if we had root 2 minus plus 1, right? Um, what we can do is we can kind of then consider the kind of the negative version. So root 2 minus 1, right? Um, and then we create a difference of two squares, right? So if we were to again use this sort of formula for distance of two squares, or alternatively, if we were to expand it out, but recognize that it is a difference of two squares, well, it's going to be root 2 squared minus 1 squared, right? Well, root 2 squared is just going to be 2, and then 1 squared is 1. So we have 2 minus 1, which is 1. But notice how we have removed the third when we created this difference of two squares, right? We've removed this sort of third um, because of the whole fact that we have a square root and we're squaring it, and how with a square root, squaring the kind of opposite, so they kind of get rid of the square root, right? And that is the whole principle of this whole set. That's the whole principle is using difference of two squares to make a third factor, a third part, if you will, um, become get rid of its third, right? By using some squaring. Okay. So let's have a look at that in action then. Okay. Let's have a look at these examples then. So firstly, we need to rationalize the denominator of, firstly, 1 over root 3. So again, I want to kind of apply what I just talked about of creating the difference of two squares. Um, and so I have a side on the bottom. So notice I can, to illustrate this, notice I can say this is simply 1 over root 3 plus 0, right? And hopefully then you recognise a bit clearly that I can create a difference of two squares by then timesing by sort of negative version of it. What I mean by that is instead of doing plus 3 add 0, I'm going to do plus 3 minus 0. So I'm referring to this, right? So this is we have difference of two squares. When I say positive and negative, the positive means I'm adding the two numbers, and the negative, I mean I'm taking away the two numbers. Okay, just to be clear. um, okay. So then if I times by like the negative parts, so if I take them away, so I'm going to times by root 3 minus 0 over root 3 minus 0. Um, well, hopefully then you'd notice that if I times across, again, the top and bottom, as with multiply fractions, that go to root 3, take away 0, but if we're just taking and adding 0, but that's just nothing, so I can leave that there as with root 3. And then I'm going to have root 3 plus 0, but again, that's just going to be root 3, times by root 3 minus 0, which is again root 3. Okay, and so then if I simplify this, well, then I'm going to have root 3, but then root 3 times root 3, that'll be root 3 squared. So, and again, I'm times by the same number, so I'm squaring it. So it'll get rid of the square root, so I'll simply have 3, okay? Because then that'd be root 9, which is 3, or root 3 squared, which is 3, however we want to think of it. And yeah, there's nothing more we could do there. I can't simplify the third anymore, because root 3 is, you can't do anything more with that. But the whole idea then, as you notice, I now have no thirds on the bottom. I have a third on the top, that's fine, but I have no thirds on the bottom. And because I have an integer, a whole number, that means it's rationalized, okay? So it's not irrational anymore, because remember, a third means it's irrational. So I got rid of the third, so it's become rational. Okay, so that's the whole idea. And actually, if I simplify this process here, when I just have just a square root on its own, I can kind of avoid this different. This is what's going on in the background, but I can just skip this step of difference between squares. And alternatively, I could just say 1 over root 3. I'll just times by the root, okay? And then root 3 times, well, that's just root 3. And then root 3 times root 3 again just gets us 3. And then we just jump right to the answer, okay? So you can skip right to that. I'm just explaining the whole method behind what we're doing there. The whole idea is creating a difference to squares. But yeah, so that's part A. Let's have a look at part B then, a more complicated example. We we have 1 over root 3, sorry, plus root 2. Okay, so with this example, I can't just times by root 2, okay? Because what's going to happen is I'm still going to have a cell on the bottom because 3 times root 2, for example, if I do 3 times root 2, that's just 3 root 2. I'm still going to have a root 2, so it's still going to have a third in it. I want to get rid of the third. So again, I'm going to need to times by the negative, right? I need to create a difference of two squares, so I need to take the difference, right, instead. Um, and so I'm going to have then, if I do instead of 3 plus root 2, I'm going to do 3 minus root 2. And actually, it doesn't matter if instead you did root 2 minus 3. It doesn't matter. We still create the difference of two squares at the end of the day. But I'm going to do instead, to follow the order, I guess, 3 minus root 2 over 3 minus root 2. Now, also bear in mind, it has to be the same number, top and bottom, because that will go to 1. Okay, so I'm basically saying I'm timing it by 1, is what I'm saying, which doesn't obviously change it. But obviously, I'm just scaling the fraction, so it's still the same, but I'm scaling it, right? But anyway, so that's the whole idea. So I take the sort of the negative version, right? So I'm taking them away instead of adding them to create a difference of two squares. And what we sometimes call this as well, instead of calling it the negative part, which is quite informal, but you can call it the conjugate instead. You might see that name floating around. So that's kind of the difference of two squares, for example. If I had, say, for example, again, x plus 2, no, or let's say root 2 plus 3, exactly what I have here, actually. Say we're given that, but then the conjugate of that is root 2 minus 3. Okay, so again, it's just a difference. It's the opposite way around. Because then that would give a difference of two squares if you multiply them, right? Difference of two squares, remember? That'd be root 2 squared, which would be 2. Take away 3 squared, which would be 9. Okay, so that's the whole idea. Likewise, if we had root 2 minus 3 instead, the conjugate would actually instead be root 2 plus 3. Okay, but that's just the language that if you see that floating around, but that's the proper way of what we call it. But yeah. So if we were to continue, if we were to carry this out, then let's just times across. But 1 times 3 minus root 2, that's just going to be 3 minus root 2, right? Anything type of 1 is itself. Then I'm going to have 3 plus root 2 at 3 minus root 2. Now, again, you could recognize it's a difference of 2 squares, but let me actually carry this multiplication out to really show you why it works. Well, okay, we're left with 3 minus root 2. But then if we were to expand this out then, so first let's deal with the 3 here, and then 3 times 3 be 9, and then 3 times minus root 2 be minus 3 root 2. And then here with the root 2 next, root 2 times 3 is plus 3 root 2. And then root 2 times minus root 2 be minus 2. Okay. But notice here, the 3 root 3 minus 3 root 3, they cancel because they cancel each other out. So I'm simply left with 9 minus 9 minus 2. And hopefully you recognise that it's a difference of 2 squares because the 3 squared, which is 9, take away root 2 squared, which should just be 2. And that is why it was. That's why if you times it in that way, if you times by the conjugate here, if you times it in this particular way, you very craftily get rid of the third and create a difference of 2 squares. Okay, so that goes to 9 minus 2, which is simply 7. Uh, there's not really much you could do here then, because really that's saying if we split this fraction up then, we have 3 over 7, take away root 2 over 7. Doesn't really tell you much. We can't simplify any of these, so you can leave it in any way you want. Okay. But also to explain just very quickly as well, it's good reason to do this because having a whole number as a denominator or a non-third or a non-irrational means we can much more clearly see what we're dividing by. For example, it's a lot easier to see that one divided by two, or like 4 divided by 2, sorry, we divided 4 into 2 parts, which we should know is 2. But if we had 4 over root 2, I mean, root 2 is an infinite decimal. It's very, very hard to see how we split that. So it gives us a clearer way of visualizing the division of the fraction. Okay. But yeah, let's have a look at part C then. We have, oh, uh, root 5 plus 2. Let me do that down here. Root 5 plus root 2, sorry, over root 5 minus root 2. Okay. And again, exact same price. I'm going to times by the other, or the conjugate. So if I add them instead of taking them away, okay. So I kind of flip the sign, if you will. So the conjugate would be root 5 plus root 2 over root 5 plus root 2. Okay, and then if I do that multiplication, well, it's going to be root 5 plus root 2 times by root 5 plus root 2. So I'm going to have to expand that out, but that's cool. We know how to expand that. Look at the last section when we looked at thirds. And then we're going to have root 5 take away root 2, root 5 plus root 2. Okay, well, let me expand the top bit then. Well, firstly, root 5 times root 5, that's going to be just 5, right? And then I have root 5 times root 2. That's going to be root 5 root 2. Now, you need to recognize the third law that we looked at last time. If you're multiplying two thirds, you can bring them together as one. So that'd be root 5 times 2 instead, which would just be root 10. Okay. Then I have root 2 times root 5 again. So that's going to be root 10. And then I have root 2 times root 2, which should just be 2. Okay. Then at the bottom, to deal with the bottom bit, well, again, you can recognise it's a difference of 2 squares. So it's going to be 5 squared, which is going to, well, root 5 squared, sorry, which is just going to be 5. Take away root 2 squared, which should just be 2, because again, just to reiterate, root 2 all squared, that's going to cancel out, just be left with 2, okay? And that'll be for any sort of square number. Okay. Well, 5 minus 2, well, that just simply will go to 3, right? And so then if I clean up the denominator, the numerator, sorry, well, 5 plus 2 firstly is 7. Then root 10 of root 10 is just 2 root 10. I have two lots of root 10 over 3, and I can't simplify that any further. I could perhaps could I simplify root 10? What's the factors of root 10? 1 and 10, obviously not. 5 and 2. Root 5 and root 2 aren't square numbers, so that won't help me. And that's really it. So we can't simplify this fraction anymore. Um, so yeah, I think we should be good there. Okay, I'm going to make some room for part D. I'm gonna, let me do part D here then. So then part D is saying we have 1 over um 1 over 1 minus root 3 all squared. Well, firstly, we can't really recognize what the conjugate is going to be because remember squared is times again by 1 minus root 3. So we can't recognize it straight off the bat. So well, what we're going to do, just expand it out, right? So if I expand that out, I'm going to have 1 over. And again then, so 1 times 1 is 1. 1 times minus root 3 is just minus root 3. Minus root 3 times 1 is minus root 3. Minus root 3 times minus root 3, that'd be plus 3, okay? Make sure you can't forget with that. Minus root 3 times minus root 3, negative will get a positive, right? So root 3 is just 3, okay? Then if you simplify this, I'm going to bring it over here, I'm going to have 1 over. Well, then 1 add 3 first, we add the numbers, we get 4. And then minus root 3 and then minus root 3, another 1 is going to be 2. So minus 2 root 3. And okay, then here we should be able to recognize again if we take the conjugate, so we just take the positive version. So we're going to times by 4 plus 2 root 3. Okay, and so then if I do the top part, well, that's going to be 4 plus 2 root 3. And then on the bottom, well, again, it's a difference of 2 squares, so I'm going to do 4 squared. I'm going to write this clear explicitly this time because I have a 2 root 3, so it might be a bit complicated, but I'm going to say 4 squared then, minus 2 root 3 all squared, okay? Again, that's difference of 2 squares. Um, so then the top bit I can't simplify anymore. That's just 4 plus 2 root 3. Then I have 4 squared, which is 16. Then 2 root 3 squared. Okay. Remember, that's just 2 root 3 times 2 root 3. So again, firstly, 2 times the numbers together. We're going to have 4. Then root 3 and root 3 is just going to give us 3. So 4 times 3, which is 12. So that would be minus 12, which would give me 16 minus 12, which is 4. Okay, and then if I could potentially simplify it, so by splitting the fraction. So this is rationalised now, but I could simplify it potentially. So I have 4 plus 4, 4 over 4. Add let me get rid of this now. 4 for 4, add 2 root 3 over 4. Well, 4 over 4 is just 1. And then 2 over 4, well, that'll just be a half. So I'm going to have a half root 3. Or I could just say that's root 3 over 2. Okay, I could put that in the numerator instead. That's, I guess, a bit more of an easier form, a simplified form, but it doesn't really matter. This is essentially the final answer, right? It's 4 plus 2 root 3 over 4. Okay, and then that should be it. It should be rationalised because there's no stud. And that is essentially the whole idea, essentially, is uh, times it by the opposite sign, so what we call the conjugate, right? Which will give us a difference of 2 squares. And if you're not confident, what you can just expand it, and like we did in the earlier on, you can expand it, and it should simplify to a number, right? So in this case, Part B, 3 plus root 2, 3 minus root 2 will always give us 7. You can expand that if you're not confident, but we can recognise that's the difference of two squares. Again, remember that's in the form x squared minus a squared. Okay, that we looked at the very top of the section here. Okay, so let's try and look at some more examples then. So now we need in this exercise, we are told to simplify 3 minus 2 root 5 over root 5 minus 1 in this form here. Notice how there's no fraction. So, well, we need to get rid of the fraction, so we're going to have to kind of rationalise the denominator, right? And in general, when you do recognise the denominator has a surd like this, it's probably best to rationalise it anyway. So yeah, so let's go along with it. So again, we're gonna have to times by the conjugate, so the opposite sign of the bottom bit. So root 5 minus 1, I'm gonna want root 5 add 1, right? And that'll give us a difference of two squares. So then if I times the top and the bottom, I'm going to have 3 minus 2 root 5 times by root 5 add 1. Then at the bottom, I'm going to have root 5 minus 1 root 5 plus 1. So then, firstly then, if I expand the top part, so firstly 3 times root 5 is just 3 root 5. And then I'm going to have 3 times 1, which is going to be just 3. Then I have minus 2 root 5 times root 5. Again, check this, minus 2 root 5 times root 5. Well, I'm going to have minus 2, lots of root 5 times root 5, which should just be 5. So minus 2 times 5 is just going to be minus 10. So I'm going to have plus 3 minus 10. And then minus 2 root 5 times 1, that's just going to be another minus 2 root 5. And then the bottom, again, I'm going to have difference of two squares. So I'm going to have root 5 squared, which should just go to 5, right? And then minus 1 squared, which is going to be 1. And that will go to 4, okay? So because 5 minus 1 then goes to 4. Okay, cool. So let's clean up the top bit a little bit. So if I do it here, well, firstly, let's deal with the numbers, right? I have 3 minus 10, which is going to be minus 7. Then I have 3 root 5, take away 2 root 5. Well, that's just going to be just 1 root 5 or root 5. And that's all over 4. Okay. Um. Okay, so that's rationalised. We can't do anything more with that. Was asked us to put it in this form. And notice how there's no fraction. So I need to get rid of this fraction part. So I think the best step actually is probably to split up the fraction. So we're going to have then minus 7 over 4 firstly, add root 5 over 4. Okay. And actually, this is in this form now. P plus Q root 5. And they told us P and Q are rational numbers. So that doesn't mean they're a whole number necessarily. It just means a rational, at least for now. Essentially, just means a fraction of it, a fraction with a whole number on the top and bottom. So, for example, 2 over 3 is a rational number. 4 over 9, even negative 5 over 1, which will just be minus 5, but that's still a rational number. But when we start introducing like thirds, for example, so if we have like root 2 over 4, well, that's no longer an integer because root 2 is, an irrational number. It's an ongoing decimal. Again, put that in the calculator. So that would not be a rational number, as we call it. Likewise, you've got other stuff like pi. Pi again is an irrational number. You should have seen at GCSE quite a lot. If you had like pi over 3 or anything like that. Well, actually, it's essentially then a fraction. A rational number is a fraction with whole numbers. Well, actually, that's what we have here. We have we have a whole number fraction here of minus 7 root over 4, and then I have root 5 over 4. Okay, well, root 5 there, but that's just for root 5 times by number q. Well, let's split this up. So if I have minus 7 over 4, and then let's get rid of the root 5. Well, not rid of it, but let's pull it away from the fraction. How we can do that is just say 1 over 4 times by root 5. And now, therefore, the quarter is another fraction and the rational one. So actually now we're good. We've got it in this form. So then if we were to compare it to the final answer, if we look here, p at q root 5, well, p is going to be minus 7 over 4, and q is 1 over 4. Okay, so hopefully you recognise what we've done there. And yeah, that's essentially all it is. Again, it's the exact same process. Look for the conjugate by essentially changing the sign of the what's on the bottom with the third, and then you get a difference of two squares, and there we are. Okay, now I want to finish off looking at some exam questions relating on this topic, and to really test your knowledge and make you comfortable with exam practice. Okay, so this exam question. Firstly, it's asking us to solve this equation, writing it as a third in its simplest form. Okay, so we're going to have x root 2 take away root 18 is x. Now, how do we solve an equation normally? Like, for example, like this. Well, we want to collect all the x's on one side. We want to get x on its own, right? I have x's in two places. I'm going to need to move the x's to one side of the equation. So I'm going to probably move the x on the right side to here. So to do that, I'm going to take away by x on both sides. So I'm going to have x root 2 take away x, take away root 18 equals 0. Okay. Well then, the next best thing is actually to move everything else to the other side. So root 18 is not tagged to an x, so I'm going to move that to the other side. So then x root 2 take away x is just going to equal root 18. Okay. Well then, I've got x's on one side and just x's. Well then I could factor an x out. Again, think back to factorising earlier. X is common to both terms, so I could say x. Pull out an x and say root 2, take away 1. Okay, hope you recognise we can do that. And that'd be root 18. But then what we can do is, well, this is a multiplication. I'm saying x times root 2 minus 1. To get just x on its own, I can divide by root 2 minus 1 to then get x is root 18 divided by root 2 minus 1. Okay, but it's asked us to write it as a third in its simplest form. Well, that's not simplify because it's we need to rationalise the denominator because we have a third on the bottom. How are we going to do that? Well, we're going to apply what we just learned to rationalise it. Well, I'm going to want to times by the conjugate on the bottom, aren't I? So I'm going to times by, instead of the negative here, I'm going to times by the positive of adding them instead. So I'm going to do root 2 add 1 instead of take away to create a difference of two squares on the bottom. Okay. If I do that, with added brackets, if I do that then, again, if I do this multiplication, let's multiply again the top and the bottom of both fractions. I'm going to have root 18 times by root 2, add 1, over root 2 minus 1, root 2 plus 1. And then again, then if I multiply, expand the top part then, first of all, I'm going to firstly have root 18 times by root 2. Again, I can bring that together as 1 to be root 18 times 2, which is going to be root 36. Well, actually, what do we know about root 36? That is 6 squared. Well, it's 6, because 6 squared is 36. So actually, root 36, first of all, just goes to 6. Then I'm going to have root 18 times 1, that's going to be root 18. And then that's the top bit dealt with. And then the bottom bit, again, because we have a difference of two squares, it's simply going to be root 2 all squared, take away 1 all squared. So that's going to be 6 over root 18. Over, right, root 2 squared is just 2. Take away 1, so that's just take away 1, which is going to be 1. Well, actually, if you divide it by 1, that's just itself, so it's just simply 6 plus root 18. So that is x, okay? So remember, x is here, x is there. But then as a final answer, it asks us to answer in its simplest form. So it needs to check if we can simplify the third. Well, root 18. Is there, what are the factors of 18? What are many square factors that we can use to simplify it? Well, root 18, well, 9 and 2, right? Because then 9 is 3 squared. So I can say that this is equal to 6 add root 9 times by 2. I could say then that's going to be equal to 6 add root 9 times root 2. That's going to be 3, lots of root 2, right? And that is fully simplified. We can't simplify the root 2 anymore. So there we are. Cool. That is our final answer. Um, there we are. Cool. Then for the second part, I'll probably have to do it on the left side here. Then we're going to solve this equation here. 4 of 3x minus 2 is 1 over 2 root 2. We actually looked at a pretty identical example to this last time, I believe, but it's good to practice more. And hopefully you start to recognise a good few questions actually are quite similar in the exam. So if you start to learn, pick up the ideas and the method, you're in a good spot. Okay, so what we're going to do here, well, we could just times, I get, you could, well, what's the main step with this sort of question? Is if we're dealing with like indices and different bases like this, we probably want to convert everything to the same base, right? So then we can easily compare it. Because if I have 2 to the something, if I 2 to the A equals 2 to the B, then clearly A has to equal B. Okay, that's the whole idea. Because then we can extract an equation with this that we can solve. Okay, so firstly, clearly 2 is probably going to be what I want every single number to be in. So firstly, the 4. Um, 4, well, 4 is simply 2 squared. So I could say 2 squared and literally put it in 4 raised to the power of 3x minus 2. That's exactly the same. And that's going to be equal to, then 1 over 2 root 2 now, you could say perhaps, well, root 2 is 2 to the half. Then you could do 2 times 2 to the half and then go from there. But I want to practice our rationalising skills. So I have 1 over 2 root 2. I have a root on the bottom, a third. I want to rationalise it then, probably. So again, I'm going to times by, well, there is no plus or minus. It's just root 2 this time. So again, I could just simply times by root 2 over root 2. Because, again, if I times by the same number, that's squaring it, so it'll get rid of the square root. So then that'll be root 2 over, well, 2 times root 2 times root 2. That's 2 times 2, because root 2 and root 2 would be 2. Okay, loads of 2s there. But then 2 times 2, after all, that'd be 4. Uh, but actually, I want to leave it as 2 root times 2. Because then, actually, well, root 2 again, as we discussed earlier, remember the index law, root 2 is 2 to the half. Remember, if I have a square root of anything, root n, any number n, that's n to the half, remember. So that's 2 to the half. Then I have 2 times 2, but that's 2 to the 1. Remember, both of these are powers of 1. So if I'm times the two numbers with different powers, I add them. So that's going to be 2 to the 1, add 1, which is just going to be 2. So it's 2 squared, okay? But then, actually, I can then say that's going to be 2 to the... then, if I'm dividing with the same number with different powers, dividing this time, I subtract the powers. So I'm going to have 2 to the half take away 2. So then a half take away 2. And remember 2, we can say 4 over 2 instead to get the same denominator. That's going to be minus 3 over 2. Okay. And there we are. That's a pretty that's a number, right? That's a pretty simplified number. So then let's just have a look at the left hand side then. So here I now have a bracket raised to a power. So then if I remember the third law here, a to the I don't know, n to the power m, I times the powers together. Okay. A to the n to the m is a to the n. So that's exactly what we'll do here, because we have a whole bracket here, 2 squared, raised to a power, even though it's an ugly power, but it's still a power. I can times the indices together, so that's going to leave us, I'm going to do it here. No, I'll do it here. 2, then, 2 times, if I times the powers, we're going to have 2 times or 2 lots of 3x minus 2. If I then expand it, well, I have 2 to the, well, 2 times 3x is 6x. And then 2 times minus 2 is minus 4. And now notice I have exactly the same base. Remember the number, the big number, right? That's being raised by power, but different powers. Well, then the powers have to, if this is equal to each other and 2 is equal, well, then the powers have to be equal for that to happen. So therefore, I can equate the powers, like I kind of discussed a few minutes ago. 6x minus 4 then has to equal minus 3 over 2. And so 6x then, if we then add 4, we're going to have 4 take away 3 over root 2, 3 over 2. And then I could put that in the calculator. I guess quickly now, I'll do it manually. Well, 4, then it's going to be 8 over 2, right? To get a common denominator of 2. But then that'll just be then 6x is 8 take away 3, which is 5 over 2. Okay, well then 6x is that, well then simply x is going to be divided by 6, right? So 5 over 2 divided by 6. Well then, if we're dividing, remember you can kind of fit like KFC, if we back to GCG, see how we divide two fractions. Well, we're going to keep the first fraction, change the sign 2 times, and then flip the 6. Well, flipping it, so it's going to be 1 over 6, right? Reciprocal. So turn it to a fraction. Well then, if we do that, well then simply then x then is going to be 5 times 1, which is 5, over 2 times 6, which is 12. Okay, so that would be the solution to that question. Um, and the last question that involves rationalising. We need to show, and this was part of an exam question. This wasn't the whole question. But again, with the A level, you're not probably going to get a whole question based on just asking you to rationalise. But you will need the tools that we've learned in this section, which are core tools, as part of the question later on. And what you need to do in this question is show that this whole fraction here actually simplifies to this, and we're going to use rationalising to help us here. Okay, so I have then minus 6 root 3 over 1 plus 1 over root 3. So what I'm going to do here, well, actually, you might think, well, I could perhaps rationalise this mini fraction first. However, I actually think you're probably doing a bit more work. What I could instead recognise is, because I've got a fraction in a fraction, I want to get rid of all these fractions I've got going on. I want to get rid of this fraction here. I want to just be left with a numerator and the denominator. No denominator with another fraction. Okay. So what I can do then is simply get rid of this fraction. Well, I want to make I want to have a root 3 on the top as well, because then if I have root 3 over root 3, they cancel. But how am I going to do that? Well, I'm just going to times the big fraction, the overall one, by root 3 over 3. Root 3 over root 3. Again, that's times by 1 effectively, so I've done nothing wrong there. So then, well, again, the numerator minus 6 root 3 times by root 3. Wow, that's going to go to, actually, I'm going to leave that there for now. I'm not going to get ahead too ahead myself. Then I'm going to have root 3 times by the denominator, which is 1 over 1 over root 3, okay? So then if I simplify this, well then, minus 6 root 3 times root 3, that's going to be minus 6. Well, it's just going to be times by 3, isn't it? Because root 3 times root 3 is root 3 squared, which is just 3. Okay, so that's minus 6 root 3, minus 6 times 3. And then the bottom, again, now I have a bracket, I can expand it. So I'm going to root 3, because I times everything by root 3. That's why we've got this bracket here. So then root 3 times 1, which is going to be root 3. And then I have root 3 times by, so I'm going to have root 3 add root 3 over root 3, okay? Because remember, 1 over root 3 times root 3 is just root 3 over root 3. Okay, that's where we got that. So, and actually, this just gives us 1, doesn't it? And now the beautiful thing here we've got now is that there's no ugly fraction in the fraction. I've just got 2, I guess, sort of a typical numerator and denominator, which we can now work with. Well, I'm going to simplify the top bit just a bit more. That's going to be minus 18, right? Over root 3 add 1. Actually, I'm gonna so I have minus 18 over minus 18 over root 3 add 1. Well, how do we simplify this? Well, we got we got a third on the bottom, so we need to rationalize it. How do we rationalize? Well, I'm going to apply exact same process again, nothing new. Well, I'm going to times by the conjugate, so I'm going to do the negative instead. I'm going to flip the sign, so instead of adding, I'm going to subtract them. So root 3 take away 1 over root 3 take away 1, again to create a difference of 2 squares on the bottom. So then if I do that, I'm going to have minus 18 lots of root 3 take away 1 over root 3 plus 1, root 3 minus 1. Then if I do that, well, if I expand the top bit, minus 18 root 3. Take away, then minus 18 take times minus 1, that's just plus 18. Because the negatives will, two negatives make a positive. Then I have root, then that's the difference of 2 squares, but again, you can always expand it. But you should always just get the roots to count. You shouldn't have any roots. But then we get the 2 squares, that's going to be 3, right? Because root 3 squared, which is 3. Take away 1 squared, that's supposed to be 1. So then that'll go to 3 minus 1, which is 2. And then simply, let's have a look. The final answer has to be in this form. So I have to have a number factorizes with 1 minus root 3. Well, again, if you're a bit unsure, well, there's no fraction, right? So again, to get rid of the fraction, I probably want to split this fraction up and see what I can do with it. So then, firstly, minus 18 root 3 over 2 plus 18 over 2. Well, again, minus 18 over 2 goes to minus 9, and that'd be minus 9 root 3. Then plus 18 over 2, 18 divided by 2 or even, that's going to be plus 9, right? Well, then what do I notice here? I can factorize it out. I notice 9 is common. So I can say 9, and that's going to be minus root 3 plus 1. Then let's compare the answer. It says in the form k. Remember, k is just a number. It's just a it's just a placeholder, right? For a number we need to find. So k, well, we factored the 9 out. So, and then it says k of 1 minus root 3. Well, I have minus root 3 plus 1. So if I'll just switch that around, so it's going to be 9 of 1 minus root 3. It's the exact same thing. I just switched it around. Well, now that is exactly in the form k of 1 minus root 3, where clearly k has to equal 9. Okay, there we are. Cool. So yeah, I think that's a good example. The good two question examples to show when we use rationalising and sort of what's expected, right? And I think this is a good way to stretch your knowledge in this section to really test your knowledge. And hopefully, if you understand this question well, then you should have mastered it, right? But yeah, I'm going to leave that there then. So see ya.